In this video, we're going to talk a bit more about convergence of sequences. One thing we've found so far is that every time we've had to show that a sequence converges, it's been required of us that we produce the limit in advance and then show that that particular limit of the sequence satisfies the convergence definition. What we want to move towards is some slightly more general results that let us characterize convergent sequences without necessarily having to know what the limit of the sequence is. So next couple of videos are going to focus on this topic, and so we're going to step through a few different results and start building up some material in this area. And what we're going to do first is we're going to look at a particular type of sequence, and we better define what these are before we actually do that. So before we move into a theorem, we're going to look at increasing and decreasing sequences. And they mean pretty much exactly what they say. An increasing sequence a sequence is increasing if every subsequent term is at least as big as the previous one. So the picture we should have in our heads is that Sn, as we go across, either stays the same or gets bigger. That makes it increasing. And we could also say strictly increasing. If we want a sequence that absolutely goes up every time, then we'd have what we call a strictly increasing sequence if Sn is strictly less than Sn plus 1. Right, and decreasing works the same way. We can have strictly decreasing if Sn is strictly greater than Sn plus 1. And the collective word for a sequence that is either increasing or decreasing, according to the softer sense, is monotone. So if we talk about a sequence being monotone, it means it's either increasing or it's decreasing. It's not a mixture of the both, it is one or the other. So here is our result that we're going to prove, and it's called the monotone convergence theorem. So it says that if a sequence is both monotone and bounded, then it converges. What's notable about this from our perspective is that it's the first time we've got a convergence result that doesn't actually have the limit of the sequence as part of the theorem statement. So all we have to do is check our sequence is monotone and bounded, then it's guaranteed to converge. Okay, we haven't specified what the limit will be, but of course to prove it we're going to have to produce ourselves a limit. To get our head around this, why don't we just sketch a little picture of what our sequence looks like. So we know that it's monotone, so we'll just assume it's increasing. We can make the same argument for decreasing, but we only really have to do one case. And we need to produce a limit S that our sequence is going to converge to. Now there's a key word here, and that is that our sequence is bounded. Now remember, the terms of our sequence form a set. So we have a set that is bounded, which means it's bounded above, which means, according to the axiom of completeness, that it has a least upper bound. So this set has a supremum, and that seems like a pretty good candidate for what the limit will be. So use sup S as limit candidate. Right, so that's a limit candidate that we can put in, and then we just need to show that our sequence converges to it. So let's just see if we can fit a proof on this slide. So proof. We'll say let An be an increasing bounded sequence. Okay, so that's the kind of sequence that we need. We're not losing any generality really to make it increasing. As an exercise, you could translate the proof into decreasing and bounded below. But for the time being, we'll just focus on this case because it represents the other one pretty well as well. So An is an increasing bounded sequence. Because it is bounded above, let S be the supremum of An. Okay, just abusing our notation slightly because we're taking it off a sequence, but that's fine. So we've got our S, and that's going to be our limit candidate. And now we're going to just apply the convergence of a sequence definition here to show that S must be the limit of our sequence. So we'll follow our standard template, which is to say let epsilon be greater than 0. we seek n such that absolute value of Sn minus S is less than epsilon whenever little n is greater than or equal to our big N. Okay, so that's cool. We have to find ourselves a big N. That's part 2, usually the hardest bit, and then we need to show that n satisfies the property that we're asking of it. Alright, so given that S is our supremum, that means it's the smallest of our possible upper bounds for our set. Epsilon is a positive number. We need to do something with it. So why don't we take a look at what happens if we go to S minus epsilon. What that implies, if we go down to S minus epsilon here, S minus epsilon is definitely not an upper bound of our sequence because S is the smallest of the upper bounds. So given that it's not an upper bound, it means there must be a sequence term that goes above it, like this one here. And also, because our sequence is increasing, once it's gone above S minus epsilon, actually from then on, every term is going to remain above it and lower than S, or lower than or equal to S, because S is the supremum. So actually this has all come together rather nicely. All we have to do is let that be the n. So let's see if we can write that. We can write this straight into our proof. Note that S minus epsilon is not an upper bound. And again, I'm mixing up my terminology again. That should be a in here. For an, so choose n. Remember, every time I say choose, it means it's because some property of something has meant such an n exists. So choose n such that an is greater than S minus epsilon. And that should be a capital N. Okay, guaranteed because S minus epsilon is not an upper bound, which means there must be something in the set that's larger than it. And this is also the capital N that we're going to have for our convergence. Now, if n is greater than or equal to n, an is greater than or equal to an, as an is increasing, and also an is less than or equal to our supremum, hence absolute value of an minus S is less than epsilon. Okay, so every point beyond this one here is within this band, and so that is what we require. And hence our sequence converges to its supremum. Okay, our next result is to do with subsequences. And before we can state it, we need to define what a subsequence is. So we've got a sequence of real numbers as usual, and now I've also listed together with that a sequence of increasing natural numbers. Okay, strictly increasing. It's just a fancy way of specifying this thing called a subsequence, which is what we get if we just take a certain subset of the indices maintaining the order. Okay, so the key point here is order is maintained. That's why we've got this slightly careful setup about m1 through to n whatever. Order of terms is maintained. Okay, so that's called a subsequence of our sequence. It's infinitely long, just like our sequences, and the order of terms is maintained. Okay, so we do not reshuffle them, we just take a strict subset and throw away the rest. Okay, and we denote it a in k, and so k goes from 1, 2, 3, 4, 5, and is the index for our subsequence. So let's look at a quick example. So if our sequence AN looks like this, if we have AN is, let's just make the sequence 1, 1/2, 1/3, 1/4, 1/5, etc. Then we can add some subsequences. We can throw away as many terms as we like, so long as we keep an infinite subset of them. So for example, we could have 1/2, 1/4, 1/8, 1/16. That's a subsequence because every term can be found in our original one and we haven't reshuffled them at all, so give that one a tick. Another one might be 1/10, 1/100th, 1/1000th. Again, they all fall within our original sequence, even though maybe it looks a bit different. And so these all count as subsequences of our original sequence 1 over n. So the next theorem may be a little bit unsurprising, and that is that subsequences of a convergent sequence must converge to the same limit as our original sequence. Right, so let's dive straight in and see if we can have a go at proving this. Okay, so we'll take ourselves a convergent sequence. So assume that a sequence AN converges to A. That's just an economical way of saying let AN be a convergent sequence and let A be the limit of such a sequence. We can just say assume the sequence AN tends to A, and that will kind of give us all the context that we need. Right, so what we want to do is we want to set up a subsequence. So let ANK be a subsequence of AN, and we want to show that ANK also converges to A. So let epsilon be greater than 0. We seek, okay, I'm doing the sleepwalking part of the proof, we seek n such that absolute value of ANK minus A is less than epsilon whenever n is greater than or equal to n. And we want to use the convergence of A somehow to do this. Well, actually, it's really easy. We're just going to choose the n to be the one that makes AN be within epsilon of A. So I'm not even going to bother writing this separately this time because it comes out pretty quickly. So choose n. Whenever I say choose, it's because some property of something is guaranteed that this exists. So choose n such that if little n is greater than or equal to it, absolute value of the original sequence minus A is less than epsilon. Okay, so remember epsilon has been fixed. We have choice of n, and we're using the convergence of A to choose a specific n, and that's what properties this particular n has. And now we need to demonstrate that our choice of n will make ANK minus A also be less than epsilon. Okay, so we've got to notice that NK is greater than or equal to K. Why is this? So if I've got K as 1, let's just draw a little table. Maybe I do need my little scratching area. Draw a table here, K equals 1, 2, 3, 4. And then we've got N1, N2, N3, N4 along here. The requirement on the n's is that they are an increasing sequence of natural numbers. And they can jump, whereas the k's can't. So it's definitely going to be true that at worst, the k's are just the entire sequence, and n1 is just equal to 1, n2 is just equal to 2, n3 is just equal to 3. But as soon as there's a double jump, for example, if n3 is equal to 4, then n4 is going to be 5, n5 is going to be 6, or larger than 6, etc. And so always we have the nk is greater than or equal to K. So if K, and this should be, sorry, and just go back to your proof, it should be whenever K is greater than or equal to N, because K is the index of my sequence. So if K is greater than or equal to n, then nk is also greater than or equal to n. Okay, because nk is larger than k, or at worst equal to it, and so if k is bigger than n, then so too is nk. Hence, a minus a is also going to be less than epsilon, because nk is further along in the sequence than k is, and so ank has also got to be less than epsilon away from a. And the subsequence ank converges also to a. Okay, so all I'm doing is just noticing that I've got my sequence convergence here. Here's a. I've gotten to this point where it's converging, and I'm saying that every term in my sequence beyond this point is within this band, a plus or minus epsilon. And it also follows that the corresponding term of my subsequence is going to be even further down this track, and so that also is going to converge to a. Right, so we'll take a break from our theorems to do a couple of interesting examples. So this one here is to show that if I've got a number between 0 and 1, then a to the n converges to 0. Handy result to be able to refer to, but we should see how we can use our subsequence answer to actually prove this. So let's have a look at what we've got first off. We'll look at the sequence a to the n. So we've got a is the first one, a squared. Now a is going to be greater than a squared because we're just multiplying two inequalities together. So we can use our inequality results to generate this chain of things here. And because nothing is negative, we're going to remain above 0 the whole time. So this sequence has a couple of useful properties. It's worth, whenever we see a sequence, seeing if we can say anything useful about it. First off, it's decreasing. And also, it's bounded below. Okay, now that actually are the two conditions required to use the monotone convergence theorem. Okay, it's bounded and it's decreasing, therefore we can use the monotone convergence theorem. Okay, remember the monotone convergence theorem says that such a sequence converges. It doesn't tell us what the limit is, but it says there is one. So by the monotone convergence theorem, this sequence converges to some limit L. Okay, we don't know what it is yet, but we know that such a thing does exist. Okay, and it's going to satisfy 1 is between it, A, and 0. Okay, so what if we look now at a subsequence? This is kind of tying everything in together. If I take the subsequence where I take every second term, so that will look like a to the power of 2n, this must also converges to the same limit as we just established. But this subsequence can also be expressed in terms of our original sequence, as the nth term, a to the 2n, is just equal to a to the n squared, which means the limit of a to the 2n is equal to the limit of a to the n times the limit of a to the n. This time I'm using the algebraic limit theorem, so I'm pulling together lots and lots of our different results. So this is by algebraic limit theorem. And so we have a to the 2n has the same limit as the original sequence, so it's going to be L, has got to be equal to L squared. L squared, That's cool. And finally, what possibilities does that give us for L? Well, that means if we were to solve this the regular way, L squared minus L equals 0, we get L minus 1 equals 0. Either L is equal to 1 or L is equal to 0. Clearly it's not 1 because of what we wrote up here. So our limit has got to be 0. This implies that L equals 0. So that's quite a nice little roundabout way of coming up with this result without having to do our convergence of a sequence definition directly. So we used quite a few things all put together. First off, we used the monotone convergence theorem to guarantee that we have a limit. Then we used the fact that subsequences converge to the same limit, that was here. So first one, monotone convergence theorem gave us the limit. Subsequence theorem gave us the fact that it converges to the same limit. Clever trick led us to L equals L squared, and then that gave us that L had to be equal to 0 because 1 is forbidden. The subsequence argument is actually really useful also for showing when a sequence diverges. Just remember that diverge means doesn't converge. So rather than trying to argue with the negation of the convergence definition for this one, easier result to use is the subsequence one. So we have two subsequences. First one is just the one that's got all ones in it. These are kind of obviously good choices for subsequences. And our second choice is going to be this one here, when we take every second term the other way. And that one converges to -1. But we know that sequence limits are unique. Okay, so our sequence only has one limit, and that any subsequence of it must converge to that limit. And so the fact that we've got two subsequences converging to different limits shows our sequence itself doesn't converge. Because subsequences converge to same limit as sequences, our original sequence must diverge. Because if it converged, then any subsequence we chose would have converged to the same limit.